Moving on to question 2, we have ethane dioic acid, which is actually your AS case study under carboxylic acid. So you can check the syllabus or any Cambridge endorsed textbook and you will see that I am not lying. It is in the syllabus from 2016 onwards, of course. If excess aqueous potassium hydroxide is added to this acid, so potassium hydroxide is basic, or you call it alkaline, you add it to acid, then you will get neutralization. Not too surprisingly, it's a dioic acid. It's got 2 carboxylic acid. That's why you need 2 of the hydroxide, because one KOH only has 1 OH minus. You need 2 of these and you produce 2 water, where you will get the salt. The salt is going to be the dicarboxylate, so O minus, K plus and K plus. That's why you have K2 and then C2O42 minus, which is an ethane dioate ion. If a small amount of potassium hydroxide is added, if you have excess, you see previously they mentioned this thing excess, then you will get full neutralization. However, if you use a small amount, you only get partial neutralization, and therefore not all the H plus come off, and therefore not all the H plus get replaced by K plus. Instead, you get an acid salt which crystallizes. So what they're saying is, if not all, there are 2 H plus, if not all the H plus come off, you could get partial. So they are not telling you the exact number. It could be whole number, but it could also be not whole number, because this is reading the question. May not necessarily be whole number. It may not necessarily be whole number. It could be any number which are not necessarily whole number. The relative number of water molecules associated with one formula of the compound. So this whole thing is 1 mole. This whole thing is d mole. So 1 mole of this whole compound has d mole of H2O. So one molecule, one formula of the compound has d mole of water. So the ratio of water molecule, the ratio of mole of water to the mole of these is d over 1. So a student, presumably you, attempted to determine the values of A, B, C, and D in a sample of an acid salt. So we don't know A, B, C, and D. A, B, C, not necessarily whole number. So be careful. They did say A, B, and C not necessarily whole number, but they did not mention about D. So D can be whole number, but A, B, and C are not necessarily whole number. They are just the ratio of the number present. Question A, a student wants to make 250.0 cm cube. So this is the classic making up a stock solution. Speaking of which, there is an experimental tutorial video series on my channel. It's on the experimental video playlist where I actually did show you an example, actually demonstrate in terms of the apparatus used and explaining all these steps by making a stock solution of something else, which is not this one. But this is basically the idea of making a stock solution. This is starting from the solid, which was what I had done in the tutorial video, so you can check out that video and it will make more sense to you if you could see what is going on if you've never done this in the lab before. But I believe you must have done this because you would have done paper 3 practical study before. Okay, so this is solid. You already weigh out this much mass. You put it into a beaker first. Describe the next step. So this one is done, so you are there already. Okay, so the next step you would do, as they said, use a series of numbered steps. This is to be clear exactly on what to do. Okay, so this thing is already in there, and then you gotta add distilled water. You never ever use just water. You never ever use tap water. You have to specify you add distilled or deionized water, because there are no dissolved ions, because you do not want to introduce other foreign ions into your stock solution. You want it to be pure, just dissolved in distilled or deionized water. You do not want any other dissolved ions, which are dissolved in tap water actually. Okay, so to the beaker. So you wanted to make up a total of 250.0 cm cube. So I could say roughly I don't know, roughly 100 cm cube. So I'm not trying to be accurate. You don't need a burette, you don't need a pipette, you just pour around 100 cm cube of distilled water to the beaker. And what you do really is stir the mixture to dissolve well, to dissolve the solid. So this is the solid already in the beaker, right? Okay, so the solid of what is that, KaHbC2O4 C.2H2O. And then what you do is pour or transfer all of the solution mixture. So you already try to dissolve as much as you can, so pour all of them into a 250.0 cm cube volumetric flask. So this is making a stock solution. They're very particular. The volume that you want is not always 250.0, but here, because you read the question, they did say you want to make it out to 250.0 cm cube. So I use a 250.0 cm cube volumetric flask. What else? Wash. Just because we try to dissolve as much as possible, there could be some residual solid still left in the beaker. So wash the previously used beaker, or you can just say wash the beaker. And just like we used distilled water just now, so we will use small portion or small volume of deionized or distilled water. Just choose one really. I don't know why I do both of them, I guess to show you. I don't know, 2 to 3 times 10 milliliter, and then each time combining the washings into the volumetric flask, into the 250.0 cm cube volumetric flask. The idea is to try and wash or get all of the solid that you're trying to dissolve in more small portion of water. Remember, around 30 ml, around 100 cm cube or 100 ml, it still hasn't reached 250 yet. Okay, into the thing there. So we combine the washing. So now we are ready. We need to add or make up to 250 cm cube mark on the flask, on the volumetric flask. I'm just going to stick with distill now instead of writing distill or deionized water. You can choose either one you want, but stick with one just to be happy. Make it up to 250 cm cube mark on the flask distilled water. Be careful at the end. Be careful towards the end, towards the mark. Add drop by drop. Add drop-wise. Add water drop-wise. Add the distilled water drop-wise. Because you don't want to overshoot the mark. You really need to be careful, because you cannot overshoot and take out again, because they will have changed the concentration. So to avoid going over the mark, you will just add until before the mark, then you do it drop-wise. Okay, after that, once the mark is reached, stopper the flask. So put a stopper on it. Shake to mix well. You gotta shake it to mix well. So usually people invert it up and down, and for that 4 mark, it's just really making out the stock solution. You can catch my experimental tutorial video on making a stock solution. The steps are going to be similar, it's just the solid that are different, and the mass was already given in the question. Sometimes you are also asked to do some sort of calculations to calculate what is the mass required to make up a solution of specific concentration. You will have seen it if you do some more paper 5 questions, where making a stock solution is a very, very popular question. Am I missing something else? Give the name and capacity. Okay, I should have gone through it just now. Describe the next step, which I did. Give the name and the capacity of the apparatus. So there's only one which should be used, and describe how the volume is exactly 250.0 cm cube. So we don't use burette to make it out 250.0 cm cube. but there is a mark. There's a mark on the flask, so make it up to the 250 cm3 mark, and we have to be careful to add it drop by drop towards the end, so that we get exactly 250.0 instead of overshooting it, or you know, overshooting it is worse. If you don't have enough, then you could tell if it hasn't reached the meniscus level for the reading on the volumetric flask mark. I already give the name, I already give the capacity. These are standard in every single description to make up the stock solution. For that 4 marks, I don't think you want to lose any of them at all. Now this is the real underlying procedure. Ethane dioweight ions react with manganese 7. This is actually in your AS organic chem syllabus. They could ask you this in paper 3 because it is in AS organic chem under carboxylic acid syllabus. Don't believe me? You can check it out and convince yourself that, you know, Cambridge does not lie to you, and when it comes out, if you don't cover your syllabus, you cannot blame Cambridge at all. MnO4 minors are very deep purple in color, so very dark, intense in color. Every other thing appear colorless in comparison with this very intensely colored solution of manganese plus 7. That's why it's called manganese 7 ions. The reaction takes place at a temperature of 70 degrees Celsius, so this requires a bit of heating, or you can think of water bath. We are not going to heat this directly on a naked flame because it will be too intense of fire. We can just use a water bath to heat it up, to warm it up. In fact, it's not boiling, it's just warming it up. Now you do a redox titration using the following steps. You gotta rinse and fill a burette. And remember that when you fill a burette and when you do rinsing, you never ever use water. Never ever use deionized or distilled water. You gotta rinse burette use the solution instead. You always rinse burette with the solution instead, because if you have any little bit of water inside the burette, it will affect the concentration of this thing that you're going to fill the burette with. And if it affect the concentration, it will affect the mole of whatever is in the burette that passes out, and therefore it will affect the amount or the volume of your titer that comes from your burette to react with whatever is in the conical flask, whatever you have pipette out. Step 2, student uses a pipette to transfer that solution A that you made up in the previous step. Okay, so this is your solution A. So make out that stock solution. You use a pipette to transfer out into a conical flask. You add this much thing, which is excess of sulfuric acid. So the sulfuric acid is just there in order to acidify the manganese 7. That's why it's called acidified manganese 7. Without the acid, the manganese 7 does not work or does not act as an oxidizing agent. You know that from your AS organic as well. When you write the reactants and conditions, if you just write potassium manganese 7 as an oxidizing agent, it's not accepted at all. You always have to have the acidified manganese 7 ion as the oxidizing agent for that same reason. Now the conical flask is heated until a temperature about 80 degrees Celsius is reached. So they do heat up the conical flask straight away. I would have thought that we could have used water bath to be a little bit safer, but I guess if you are doing this as part of titration, you really want to save time. And this question has actually come out as a paper 3 titration. It's one of the more difficult titration to do. This is a hot conical flask. It's quite hard to handle, alright? So a lot of people can get very clumsy if this actually come out in paper 3, but you never know if it will come out in paper 3 or not. Okay. Step 5, the student adds MnO4 minus from the burette until the endpoint is reached. So you do not need an indicator for this kind of reaction because the color goes from very intensely colored to almost colorless. Because of the very clear, very sharp change in color from deep purple to colorless, you don't need any other indicator for this at all. Now the student repeats the titration until concordant readings are achieved, which is very standard, right? I mean, if you look at any marking scheme for paper 3 or paper 3 O-level, IGCSE or even A-level, they always say repeat, or the students will get concordant reading. That means consistent. And for A-level, For A level, you know the standard is plus minus 0.05 cm cube. That's why your level accuracy must not, your best titer cannot be more than plus minus 0.10, because your titer come from 2 readings of burette. Therefore, they cannot be more than plus minus 0.10 apart. Since this is your rough titer, you see, you always do a rough titration. Doesn't need to be exact, but it's for you to know where about you want to fish, okay, where about the endpoint is going to lie. So the student determined the average titer to be 24.40. It seems like the student picked that and that. This is too far away. This is 26.5. It's not 24.5. That's why you only take these 2 readings. When you average them, you always have to be appropriate in your amount of significant figure, because it's the average titer, and all your titers come from burette reading. They are to 2 decimal place. Okay, for A level burette readings, 2 decimal place. That's why the average is also 2 decimal place there. When emptying the pipette in step 2, the student touches the surface of the solution. So this is emptying, and then you kind of tip the pipette into the flask. Suggest why the student does this. If you have done titration before, you usually would do this, but you don't try to tap so hard that you break the glass. Typically, people usually tip like once or twice, not more than that. That's just to get the very last drop of the solution, which is in this case your pipette. What did you pipette out? You pipette out solution A. In this case, solution A from the pipette into the conical flask. So even if you tip like so many times, there's always going to be the very tiny drop. So this last drop is probably going to be one of the bigger drop, but there's always going to be like 1 tiny drop or 2 tiny drop, which are not as big as this last one that will come off when you tip them off. But those are already taken into account by the error accuracy. So each apparatus come with an error already in them. So if you look at the pipette next time, you will see there's a plus minus something cm cube, and those actually take care of the very last drop that you can't get out from the pipette at all. But you could try and get as much out as possible by tipping off the end of the pipette onto the glassware. You don't do it very hard, because glass on glass, they easily break, okay? So just be very careful there. So we're going to measure out the H2SO4 in step 3. So as I mentioned just now, step 3, so you have an excess of H2SO4. They don't say 20.00, they don't say 20.0, they just say 20 cm cube. It's in excess. It doesn't really matter that much. So you can use a measuring cylinder. That's very common to add something which is in excess anyway. Okay, so it's just the most appropriate amount of appropriate piece of apparatus. This is commonly what you do in paper 3. So what makes it any different when you have to tell someone or describe to someone how you would do it? Now suggest why the student starts each titration with an initial burette reading of 0.10. If you have done any experiment involving any titration involving this MnO4 minus, you know this deep purple in color is really not a joke, okay? You can't read when it's very intensely colored at all. You can't read the lines on the burette. That's why we always make the reading, when we do the initial reading on the burette, when we're dealing with this, we always feel below 0, okay? My personal favorite is 1.00. But anyway, that's my personal favorite when I do this. You don't have to start with 1.00. You can start with things like 0.10, but at least you could read what is above it. And essentially, when we do experiments or titrations, when we do titration involving MnO4 minus, we always read above the meniscus. Okay, because you read above the meniscus here, you will read above the meniscus here. You read above meniscus, you read above meniscus, so this reading will still be correct. The same way, you will read below meniscus for something which is not intensely colored. Okay, only for something which is very intensely colored, because we have to read above the meniscus, we cannot possibly start from 0.00. Okay, so very intensely colored MnO4 minus aqueous ion makes it difficult to read readings on burette. So we read below the meniscus, above the meniscus. So 0.10 cm³ can be visibly read, I guess. Okay, so you can read the 0.10 cm³ visibly, but if you fail to 0.00, you can't read anything above it at all. Okay. Now, what is meant by concordant readings? In the context of A-level chemistry, you want it to be consistent. So this is consistent and consistent. But in the context of A-level chemistry, due to the error in a single reading for burette, your accuracy must be, so your accurate titers come from initial and final reading on the burette must be plus minus 0.10 cm³. So concordant and consistent titer. Concordant titer mean consistent titers that are within plus minus 0.10 cm³ in the context of A level. Back in O level, your burette reading was read to 1 decimal place, and therefore your accurate titer were accepted to 0.20 cm³, but not in A level, where you are demanded of a higher certain level of accuracy here. So it means consistent titers or titer readings that are within plus minus 0.10 cm³, and this is due to error in a single reading for burette. In a single burette reading is equal to plus minus 0.05 cm³. So this is not really required. So if you take one reading on the burette, there's an error of this plus minus 0.05, and this is your other reading plus minus 0.05. So your maximum error in a single titer is going to be plus minus 0.10. So your level of accuracy has to be consistent to plus minus 0.10 cm³ for it to be concordant titers. State the change of color in the mixture in the conical flask at the end point. So we know from the deep purple and everything else appear colorless at the end point. So it's from deep purple to colorless. Now determine the moles of that ethane diode ions in the 250 cm³ of solution A. Give your answer to 3 significant figure. Alright, what do we have? This is titer. The titer comes from the burette. The titers come from the burette, and this is actually a C2O42 minus in the burette. Am I correct? No. This is your KMnO4. This is your KMnO4. I must not get confused. This is your purple color, KMnO4. What do I have? What do I know? Determine the number of moles, and this is for 3 marks. This is really 3 marks. Okay, perhaps what I can do is I draw a simple diagram. So from the solid, I make it out to 250 cm³, solution A. So this is the solid, and then I take out 25.0 cm³ of A for titration. My titer was KMnO4 that reacts with this, so perhaps I need to start from here, then work out what is the mole of the C2O42 minus in there. So let's see what is changing and what is not changing. The mole here is the same. That is very, very important. What is changing and what is not changing. The concentration here is the same because I'm taking this out from here using a pipette. So I'm just taking out. So the concentration is the same. But the mole is not the same, because if concentration is the same, I'm taking out smaller volume, so my mole is actually smaller, my mole is different. So they haven't guided you the way they would have guided you in a paper 3 or in an AS level setting, or even in O level or IGCSE practical, because this is A level paper 5. They expect a certain level of maturity and advanced level chemistry. Okay, so you should be able to kind of like draw this kind of diagram. These are typical questions that I would have done in my topical playlist on AS mole calculation and stoichiometry. There are a 5 video series on something called backward titration, so you can check out those video tutorials out if you are not very happy with this kind of calculation. So check out those topical playlists, look for backward titration inside the AS mole calculations and stoichiometry. All right, anyway, so I'm gonna start off by looking at mole ratio. Actually, I'll start off with mole ratio. What is the mole ratio given here? I have 5 C2O4 2 minus reacting with 2 MnO4 minus. So the mole, I probably write it here, the mole of C2O4 2 minus is to the mole of MnO4 minus is 5/2. Like I said in all my other mole calculation and stoichiometry videos, doesn't matter which way around it is, I always like my bookkeeping this way because I rarely make a mistake by doing it like this. Okay, from the balance equation, on top is the ethane diode ion, at the bottom is MnO4 minus, on top is the actual mole, here on the right hand side is the actual mole that reacted. This is your titration. Okay, so this is your mole of C2O4 2 minus in 25.0 cn cube, because this is the titration in 25.0 cn cube. Because if you read the instruction just now, you take out that much only. So we are talking about the titration. This is the titration, so it's only 25.0 cn cube of solution A. How much MnO4 minus did you use? This is from your average titer. This is in the burette. The burette is the MnO4 minus. So that's 24.40 cm cube. So 24.40 cm cube. Convert that to dm cube times 10 to the minus 3. Convert this cm cube to dm cube. The concentration is 0.0200. So there's concentration in mole per dm cube times volume in dm cube, and that's the actual mole of MnO4 minus that will react with 25.0 cm cube of that ethane diode ion. So I'm going to cut that and I'll bring it down to the particular working down here. Okay, so I can just work out the mole of C2O4 2 minus in 25.0 cm cube of A. So I bring that up. That's going to be 5/2 times 24.40 times 10 to the minus 3 times 0.0200. So pop that into your calculator. And I get 1.22 times 10 to the minus 3 mole. Remember that is in 25.0 cm cube. That is still here. I want what is the mole of ethane diode ion in 250 cm cube. So therefore, in 250 cm cube, the mole of C2O4 2 minus is going to be 250/25. That's the factor. How much bigger? Remember, they have the same concentration, but the mole is different. So going from here to here, you have greater volume. How much greater is the volume? Therefore, how much bigger is the mole? Alright, this is very common in your AS level practical kind of paper as well. And you should be able to get all the 3 marks here if you know what you have done from AS as well as O-level chemistry or mole calculations. Now they say if you are unable to calculate an answer, but you should really be able to calculate something, it might be wrong, but you should be able to use the answer for the next step. Okay. The student then does an acid-base titration. So we're going to do an acid-base titration. So just now was a redox titration because you went from the MnO4 minus, which is manganese plus 7, which is deep purple in color, to Mn2 plus, which is kind of pale pink colorless in solution. So there's manganese plus 2. So that is your reduction. And this is your oxidation. This is a redox reaction. Now we're just going to do an acid-base titration, and that is to determine the value of A and B, because this is to do with the H plus swap out for K plus. Alright, remember it was partial neutralization. If you remember the earlier bit of the question, partial neutralization, it was mentioned earlier in the question. because this is acid-base titration and they want the name of a suitable reagent to use in this titration. Reagent, so it's a reagent, it's not an indicator, it's a reagent. All right, what can we use here? All right, so we need to use a base. We need a base. So I was just thinking like what kind of base would be suitable, but I just remember that the whole idea is we are swapping out the H plus for K plus, and we are trying to find not just the value of B, but also the value of A and B. All right, so we're thinking about the value of A and B. So to swap out with K plus, we really need a KOH, all right, as our hydroxide, but they want the name and not the formula. So I would imagine that you would need something like potassium hydroxide, where you could go from this partially neutralized acid salt. So it still has some of the acid, it has some of the salt, and they will go on and form the complete salt. And knowing how much potassium hydroxide is needed and knowing how much of this react, then you can find out how much acid there is remaining, and therefore how much of the K plus is actually in there as well. So this is a very good kind of question. So the student finds the concentration of H plus in solution A to be whatever that is. So that is your H plus concentration. So square bracket is typically how we define concentration. As you have known, since this is an A-level paper, you have seen square bracket to denote or to represent concentration for a long time already. Now you need to determine the ratio of C to B to 2 decimal places. So use this value to determine the ratio of C to B. So I have the concentration of H plus. Do I have concentration of C2O42 minus? I have the mole of it in 250 cm³ of solution A. So I am able to work out the concentration because this is how much mole in 250.0 cm³, and this is for ethane diowate ion. This is for C2O42 minus. So first of all, I probably need to work out the concentration of the C2O42 minus. Is going to be the mole of C2O42 minus divided by the volume. But I know the mole, and that is in 250.0 cm³, so that is just 0.0122 divided by 250.0 times 10 to the minus 3. This is mole, this is dm³, so mole per dm³ is going to be, oh no, I don't want to delete. I want to copy, I want to cut it and paste it down here. So I don't even know if I need the concentration or not. Let me think. So that is going to, so I have the concentration of these and I have the concentration of these. I think I don't want concentration. I want to keep it as the mole. I think it's better if I keep it as the mole, because I just remember something. We are comparing mole ratio. So each of these is to do with mole ratio. How many mole of K is to how many mole of H, how many mole of C2O42 minus, which is C. So in solution A in the 250.0 cm³, how much is H plus? Okay, so that is the mole of C2O42 minus, and that is from B part 4. That is the mole of C2O42 minus in solution A. Now the mole of H plus in A is going to be the concentration of the H plus. This is in mole per dm³ as given here, and that was in 250.0 times 10 to the minus 3 dm³. So what I can do is I can cross out the dm³. And I could get 0.01525 mole. So that is the mole of H plus in A. So what is the ratio of C to B? So as you could see, the mole of C2O4 2 minus is to the mole of H plus is C over B. From the formula, there are C mole of C2O4 2 minus and there are B mole of H plus, and I have mole and mole here, so I'll just put in 0.0122 mole divided by 0.01525. They want the ratio, so C over B is equal to 0.0122 divided by 0.01525. So that gives me 0.8. What is 0.8? 0.8 is actually 4:5, but they want it 1 on top. They want the C is to B is 1 is to something. So I'm going to have to think of 1 is to something. To get 1 on top, I need 4 divided by 4. Alright, so that to that is divided by 4. So that to that is also divided by 4. So 5 divided by 4 is going to give me 1.25. And they want it to 2 decimal place. So 1 is to 1.25. Alright, 1 is to 1.25 is the same as 4 is to 5 is the same as this is to this is the same as C over B. I only give it 1.25 here is because they purposely want the C to be 1 on top. Okay. Okay, what next? Then they said then deduce the value of A. How in the world am I going to deduce the value of A? Let me think. Let's try and think. Any information given? What's the value of A? Let me have a read through the earlier bit of the question. So I know the other information they gave me was 1.89 gram of that whole thing. Not exactly useful though. 1.89 gram of that whole thing. Is that useful? Let me think. 1.89 gram of the whole thing. So 1.89 gram of the whole solid. What do we started with just now? We started from C2O4 H2, didn't we? Like that. And now we know that C is to B. Okay, I think I see it. Okay, so now you have previously you have this thing here. So what would happen is this is originally like this, meaning to say for one C2O4, originally you have 2 hydrogen. Now you only have 1:1.25, right? Originally you have one of the C2O4, one of it has 2 hydrogen. So C over B originally is 1:2. Original C is to B is 1:2. But now 1:1.25. Now it's only becoming 1.25. Now partially neutralize. If you partially neutralize, then you become 1.25. Then C2O4. You still have one of it, because they purposely ask you to do the 1 there. I think I get the idea why they want the 1 there, so that it becomes 1.25. So from there, from the 2 to 1.25, how many has gone? 2 minus 1.25 is 0.75. Okay, so from H2 C2O41 to become H1.25 C2O41, and you have a K something, which is A, right? A. Deduce the value of A. Deduce the value of A. Okay, remember the H plus replaced by K plus. The H plus replaced by K plus. So you still have one. You still have 1 and 1 there, but now you have 2 going to 1.25. Therefore, A plus 1.25 is equal to 2. or rather I would say 2 is equal to A plus 1.25. So A is going to be 2 minus 1.25, which is 0.75. Remember just now they say A and B and A, B and C does not need to be whole number. So that is what they said earlier. And where was it? I remember reading about it. They say it does not need to be whole number. There you go. A, B and C represent a ratio and may not be whole number. So A and B are not whole number here. And it makes sense that K plus, H plus same charges. So I'm just replacing some of the H plus with K plus from the start, which is this ethane dioic acid, now to this partial acid salt. Some acid still present, but some of them have formed salt. Okay, if I know how much of the acid is present, then I know how much salt is present as well. Based on this being 1 and 1, then I can compare them. That was the reason why they want us to make this into 1, and even though we get 4/5 just now, we make it into 1:1.25. This and this total up to give you 2, which is originally what you have of the H to begin with. Alright, very good question actually. Now use your answer to B part 4. B part 4, what was B part 4? B part 4 was the mole of ethane dioate ions in 250 cm3. So B part 4 is the mole of the C2O4 2- in 250 cm3. How about C part 2? C part 2 has a lot of things. C over B is 1:1.25. C over B is 1/1.25, and then and A equal to 0.75. And other information, a lot of things. Yeah, other information given in the question to determine the mass of 1 mole of it. So you want the molecular mass. How in the world are we going to work out the molecular mass? Let me think. If you remember the simple diagram we drew just now, so what do we have? From here to here, the mole is the same. So I know the mole here, which is going to be equal to the mole of the solid, because all of this goes into here. The mole of the ethane dioate in here is equal to this. So I know the mole of ethane dioate. So the mole of ethane C2HAO4 2- in A is 0.0122 mole. I think I need to work out the ratio. So this is the mole of it. So now I know it's actually this is a bit tricky. So I know now is K. A is 0.75 because I worked it out before. So A is 0.75. H is going to be 1.25. And then C2O4. Those are the previous thing that we used, meaning to say C has to be 1. And then I have dot DH2O. Okay. So when I dissolve in water, because I make up, this is the solid, right? This is the solid. So the mole of this is equal to the mole of C2O4 2-. You know why? Because in this formula unit, there is 1 of C2O4 2-. So it's equal to the mole of the ion. That's it, really. I mean, in one of these, there is 1 of these. So the mole ratio is 1:1. Or you can think about the mole of C2O4 2-. No, actually, I'm not going to do that. 1 of these give you how many C2O4 2-? It give you 1 of these. That's why the mole ratio is equal. In one a whole lot of these, based on the number that we worked out in the previous question, they are going to be equal in mole ratio. 1 whole lot of these give you 1 of these. This is equal to this. Alright. Now, the mole of this in A is 0.0122 mole. And how about the one on the right hand side? Here is where I need the whole mass. I need the mass. because how much of the solid did we put in? So I have my diagram there. How much of the solid went into there? That was actually given in the question. I remember going through the mass, thinking about whether we're going to use it or not later on. 1.89 gram. Exactly 1.89 gram goes into the solution. 1.89 gram. So I have mass 1.89 gram divided by the molecular mass of this thing. Okay, I don't know D yet, but I can work out the molecular mass because I know how much mass of this, and I just want the molecular mass. 1 mole of this give you 1 mole of this. That's why I have mole of this equal to mole of that. So MR equal to 1.89 divided by that answer which I obtained from B part 4. I get 154.918. They did not specify how many, they did not specify how many what was I going to say? They did not specify how many significant figure, but based on the other bit of the questions, they did say 2 decimal place for this, but it turned out that I used 3 significant figure for my other data, so I think it is okay to give it to 3 significant figure. So this is gram per mole. The unit for MR is what is the mass for 1 mole. So the mass for 1 mole is just gram, but the unit of it is gram per mole. Mean 1 mole of that stuff has this much gram. Okay, the answer must be 155. But I'm also supposed to work out the value of D. So for this whole thing, D is the unknown. So the MR equal to 155. So 155. I don't know why I didn't just do them straight away. So 155 is the MR. So you have 0.75 times the 39.1 for the potassium. Then you have 1.25 times 1.0 for the hydrogen. Then you have 1 lot of 2 times 12.0, and you have 4 times 16.0. And you also have D molecules. You have D amount of H2O. So D times 2 times 1.0 plus 1 times 16.0. Okay, so 155 equal to, put that into your calculator, so that give me 118.575 plus 18.0 D. So D is equal to 155 minus 118.575. Make sure you do this in a bracket. If you are careless, if you are very careless and you forget the bracket, you'll be doing this divided by 18, and that will give you a wrong answer for D, which is a very big number. Okay, so do those things in a bracket because this is your primary school mathematics. Do things in fraction and do things in bracket first. So I get 2.024, and that looks reasonable. So that will just be 2 to nearest whole number. Okay, because why this is whole number? Because when you read the question earlier, of course you spotted that they said that the number of water molecules can't be fractional, and they only say A, B, and C, not necessarily whole number. They never mention anything about D. So I already shown it that, you know, experimentally speaking, it's almost impossible to get exactly whole number, but we are sensible enough to run it up to the nearest whole number because of what it means as the water of crystallization. Water of crystallization is an O-level and IGCSE concept in chemistry, and it's something that you will have done previously also. Okay, nearly the end of this paper now. For this 2-mark question, so we are using another method to determine D. D is water of crystallization, right? So D is water of crystallization, and this is a solid, and you should have known from, actually you can check out my experimental tutorial video series. One of them is called water of crystallization. You should watch that video and see what actually happened. Okay, so if you think about this formula, let me just show you. That thing So, and that thing there, C2O41 dot DH2O. So what is gonna happen when you heat it? We know everything else already, we just don't know the value of D. Okay, so that thing, when you heat it, gentle heat, it will not decompose the solid. In fact, that's probably what I'm assuming, okay, but it will give you DH2O. So it will give off this water of crystallization, and as you could see, this is 1 mole, this is 1 mole, this is D mole. Okay, so if we know about the changes in the mass, then we can work out the mole ratio, and we can work out how much water has been lost. We can work out the mole of water lost relative to the mole of the solid that we have heated, and therefore we can work out the mole ratio, and hence we can work out the value of D there. Alright, so in terms of a results table, results, so this is plural, so we need more than one readings need to be taken. Alright, so in a table, this is actually one of these things called gravimetric analysis. And gravimetric analysis is actually part of AS practical, and this is also very commonly asked in A2 paper 5. If you have done one of those older, well, not really old, like couple of years old, 5-6 years old, they are like if you have CuSO4 dot XH2O, and then you get CuSO4 dot XH2O, they ask you to plot a graph. They ask you to plot a graph of the mole of H2O is to the mole of CuSO4. Then you can get a gradient or something like that, and the gradient would basically be this over this, which is x over 1, and therefore that would tell you the formula, well, the value of x. Same idea here, just a slightly more complicated looking compound, but it's the same idea. Water crystallization is no different from what you have done, what you have understood, in fact, from alternative to practical back in O-level and IGCSE. This is also a very simple looking things from paper 5 as part of analysis and evaluation. They ask you to plot the graph. Here they don't ask you to do that. What reading do you need? Okay, so if I call this acid salt, which they did call it acid salt, yeah, okay, hydrated, and then I'll call this anhydrous acid salt. Actually, I don't call it acid salt hydrated, I call it hydrated acid salt. Alright, so a bit of English there. I would need the mass of empty tube to begin with, and then gram. I would need the mass of tube plus, meaning you add it, plus the hydrated acid salt. So don't forget that you have the unit for the measurements. All of these are using mass balance. I will rub out this thing because I really needed the space, since I already outlined the idea to you anyway. And then this is before heating, and then mass of tube plus acid salt after heating. Okay, after first heating, and then mass of tube plus acid salt after second heating, and essentially you want to heat until constant mass. Okay, heat until constant mass because you do not want there to be any more water crystallization that hasn't been driven out. Alright, so essentially what is the mass of water then? So the mass of water, the mass of the H2O is going to be whatever that you have heated to constant mass. I assume that after second heating is already a constant mass, so all the water has been driven out. And another assumption is that they do not decompose during heating. Okay, they do not decompose during normal heating, therefore they will remain as the salt. So if you have the mass of H2O, they don't ask you how to process, they don't ask you to describe the process, they just want the readings. I'm pretty sure I have gotten the marks already. I'll just very quickly show you how to process the data if you are being asked on this as part of planning, analysis, and also, well, experimental planning, I guess. So the mass of H2O is going to be, after you heat it to constant mass, minus the hydrated form, the anhydrous plus the tube minus the tube and the hydrated form. And how about the other one? This thing, the mass of anhydrous acid salt is going to be 4 minus 1. So that is your mass. You also need the MR, which you have the MR. So you have the MR of this, you have the MR of water. Then you can compare the mole ratio of H2O divided by the mole of this. It will be equal to D over 1. D divided by 1 is just D, and therefore you can use this method to determine the value of D as well, if you know the MR of this. Okay. Yeah, I think I'll just leave it there. So we don't really need to process the data. It's just about labeling what readings we need. And of course, I've just added like second heating, but the idea is heat until constant mass. You could have the third heating or the fourth heating, but it's strong heating, and you let it cool down, and then you would measure the mass. Okay, I've used a tube, but then this was how many gram just now? Not really. I mean, this is a different experiment, so I don't really necessarily need to use the exact same mass as just now. If I'm working in a tube, I can use a smaller amount, but do not forget that you can also use something called crucible. You could also use crucible, and because there is heat resistant, it's made of ceramic, they will be suitable to heat a larger amount of solid than a tube. Okay, so that's it from me in this tutorial video. That's the end of this paper 5 already. So this second question is part of experimental planning and design. Really good question, I would say. Slightly confusing, but not like the worst of all. If you try to maneuver your way around it and try to think about the underlying skills that are needed, and as well as you think about all those simple stuff that you would be capable of doing, even if you are an O-level or IGCSE students, all that thing is basically just mole calculations and stoichiometry. If you're very unfamiliar with these things, I advise you to actually check out my topical playlist. Do not just focus on paper 5 because it's paper 5, but also work on your mole calculations and stoichiometry, and for that you can check out my topical playlist. As an A-level student, you can check out the AS topical playlist on mole calculations and stoichiometry, and those things are bound to come out in paper 3 or paper 5, whether you like it or not. Alright, so don't forget to click the button on the bottom right to subscribe to the channel. So click it now if you haven't, and please share the channel widely with all your friends, your chat group and study group, your juniors and your seniors, your teachers, your wider social network, or when you plan to return to your social life after all the exams are over. So do follow me at ptet.chemistry, ptet.chemistry on Facebook, Instagram, Twitter to get connected, and let me know how the exam go, as well as when the results come out. Okay, so good luck in your exams, and I hope you all enjoy learning chemistry. And if you spot any mistakes in the paper, please let me know, because as usual, I don't really check the marking scheme. So and of course the marking scheme hasn't been released for this paper yet at the time that I'm doing this video, and at the time the video was released. Alright, so let me know if you spot any mistakes, and yeah, see you in the next tutorial video. So don't forget to subscribe. Alright, so thank you for watching.